based methods. And then after that, we're gonna have an introduction to Houdini with some basic tutorials again, and then gradually start moving towards the body and more complex surfaces. So basically, we will have three introduction examples to Houdini, and then we go for more complex cases, which are these two methods. I think the fact that we are recording the sessions would help us later on to recap if something is missing or you can't follow. We try to have a pace that everyone can follow, but for several reasons that might get basically abrupted. Therefore, yeah, if there is a question during the session, maybe you can raise your hand or comment, and then we can come back to that. We can use the comment line of the Zoom. Yeah, and that's it. And we have received your presentations. We looked on some of the presentations last night and today. We're gonna continue looking into your presentations, and then during the lunch break, we kind of make a decisions. What are the directions that we can take and how we can join forces, so on and so forth. But today will be mainly on tutorials. So let me just check. Yeah. So if Benjamin is good to go, maybe we can start with you. Okay, I'm gonna stop sharing one moment.
Just one thing, guys. Like, since we can't see everyone's screen, you don't have to raise your hand. Just let us know if you wanted us to stop and ask a question. It's fine.
Yeah. Okay, so let's have it a bit more interactive as we can. And recording, I'm gonna be mute.
Okay, so first, it's a little basic tutorial, as Sina already mentioned. Maybe go to the Google Drive folder, and in the Grasshopper, under the files, Grasshopper sample files, there's a Rhino file. Just open that and open your Grasshopper, Grasshopper as well. So you should have that here on your screen. And what I'm going to explain first is a simple method how to geo-wrap curves in that tutorial. It's with the plugin Cocoon. I think it's based on this geo-wrapper engine, which was developed earlier. So it connects Metaball with a marching cube system. So So the idea is you work along. We start here with an empty one. In the second one, I provide you already a little more, and then we quickly build this system here. So we're going to use this rectangle. Everyone should use it, so we're in the same scale. Link it with a curve, and also link that curve as an attractor curve. I'm going to use it later to distribute the geometry a little. So we can name that rectangle. And okay, what we're going to do is first make a surface out of the rectangle and populate it randomly with points. Let's say we need 30, that should be enough. If I'm going too fast or too slow, just let me know. And yeah, let's have a seed as well, so we can change later the position of the points a little, right?
Do you have one focus?
Uh-huh.
Do I have focus so they can see the logo at the same time the name?
No. Okay, you always use names. So.
I always use names also, but some people prefer
the icons. Okay, I don't know.
but you continue also.
Yeah, okay. I would continue with the names if that's okay. Okay, no, I can also use the full names.
Yeah,
No icons. Maybe that's the best for now.
yeah, so they can find.
Okay, so we have this this surface here, our points. Then we're gonna create a second set of points as well, just with a different seed. So we have two different sets, but same amount, and we're just gonna move them up a little in the Z direction. And let's say around 30 millimeters. Oops. So I have this set, that, and this. So what we're gonna do is now find the closest points from that set to this one. We need to graph that, the first one, and say let's find the 5 closest points. It's just some random grid I create here, so it's nothing special. And connect them with lines. Graph start. Oops. And here we have a random grid, whatever. So in the thing. Okay. So what else? We need this attractor curve. I think it could work there, but we could also move it to the middle. So we're going to use the same vector motion, divide x by 2, and move the attractor curve up in the middle. So let's see it now. Okay. Oh. Okay. So what else? Now we need to check. Okay, how we need this attraction of this geometry. So what I'm going to do is take the center of the curve, polygon center. So you get the center points here. Flatten it first. Sorry. And check the curve closest point. So from the center point here towards our attraction curve. So you see now like a bunch of points there, and we get the distance. And this distance is important for us because through that value we can remap these. So I'm going to remap the numbers, set the values. The source domain we can define with a bound. And the target, we just define a domain. Construct domain. And let's say from 5 to 12. That's the range of the radius for the metaball system later on. So we get now all these values. So each point now has a value in between 5 and 12. So now it gets interesting. So let me hide little stuff and lines we can use. Okay, so we're gonna now use Cocoon, and let me find it for you. It's under Mesh up here, and we have like an engine. So that's the marching Marching cubes, we need that one. We need the refine later on. And we need for now, because our base are these curves, we need a curve charge here. So what we're going to do is insert our grids here, and the radius we've mapped. So here, and the strength. So that's a factor. Let's go for 0.3. And we see we don't see anything here right now, but the curves are charged. So according to the remap values of that tractor curve. So we input then the charge, an ISO value of 0.2, and cell size, let's say 3.0. And then of course we need to run it, toggle. Run it. Then we can see already we've created this pretty rough marching cube geometry around it. So what it does here first creates the charge of the interval, and then transforms it to marching cubes, which is kind of voxel-like geometry creation. So, but this mesh is not really nice. I mean, we could say the cell size, if we reduce it, I could do it now, but I go the other way around. I say increase, because otherwise it takes forever, to 6. It's getting rougher and rougher. So let me quickly show you something. So if we now say we just take just one line here. Just this line, and charge it as well with a radius of 5.0, just as an example, and insert that in the cocoon. We see what it does if we change the values. So the radius obviously defines the radius, the strength. Get that one. You see what it does. So sometimes it's just nice if you don't have that strong, because of the radius and the remap values, you get a dense geometry. And then here we can see, okay, if we decrease the ISO value, it gets smaller and smaller, the other way around. And cell size is quite obvious, I think. So last step is then to we can use that mesh, or we can use the refinement data, plug it in there, and define how many samples we need. So we go for 50 for now. The sample size for 0.5. Tolerance could be a value of that. Smoothing, I go for 5 now. Just these values, you can use them later on as a starting point. The length 3. And the subdivisions, I would go for 2 subdivisions. I can show you in a bit first. And execution. Okay, so let me hide that. Or let's go. So here we have now our mesh, and we can see what the refinement. Okay, it shrinks, so we can help us here with the sample size. So if you increase it, it's more stable geometry. Sample, it's again the same. So if you go lower, it just uses less samples, so the geometry gets a little less defined. And smoothing is clear, I think. Wait. Smooth it more, it gets better mesh, and obviously the subdivision subdivides our mesh even more refined. So if we now then connect this back to, that will take a second. All right. Connect that guy. Wait a second. What now? We have this geometry created here. So as you can see, we can play. There are some inputs. We can play with it. So for that example, I use these values because I wanted to create something like that. So that's what you get out of it. So I think that's more or less about this geometry wrapping. It comes in quite handy. So you can also charge B-wraps, curve groups, and points. So it's a nice way to get the mesh out of the curve network. And in the next example, we're going to see one example where we can actually use it to create something out of it. So I think if you don't have any questions, or if you have questions for that, let me know now. Okay. Cool. So in the folder, there's also a Grasshopper file, so maybe open that one. In the same running file. It's already grid. No idea. It's so strange. Okay, someone is missing the folder. Sina shared the drive. It's in here. So we go to files, Grasshopper, set files, and these two files should be in there. So Lorenzo, are you good? Okay. Can you share the link of the drive again? Nice one. Okay, let's start. So again, I did some random grid here, and so we're gonna try to build on top of that. We also have attractor points which are far away. So here's the grid, one to the left, one to the right. And what we're gonna do is now introduce Culibra. It's a swarm agent system, so it works. Let me find it here in the chaos. Yeah. So this is Culibra here, you can see. So it works with flocks, with crawling systems, different behaviors of swarm systems, and so what we can do is now then use trails of the swarms, of the flocks, and combine them to geometry. That's exactly it. So you can just drop it again.
You're asking for the file folder?
Yeah.
I just shared it in the chat.
All right.
Okay, cool.
Is the file is the one which start with swarm, right?
Yeah. It's that one here. Swarm empty.
Okay.
Okay, so Libera, we have an engine here, or multiple, but we're going to use the normal one for now. And we need to introduce some settings, so some behaviors and settings, what the flock should do. We need to spawn these particles. I'm going to introduce a box spawn here. Therefore, we need a box. So we're just going to take the bounding box from our system here. Union box, of course. And then we need to, here we can, if we hover, we can say, okay, where shall these the agents spawn, on a line on the ground or randomly in the box? So I want the second one, so I go for option 2, 2, which is 1, and the count, how many agents should appear. So for now, we go for 100 or 125, something like that. We can increase it later on, but it's always easy to, or better to start low on these things. So then we have the spawn settings, and we need to connect them as well with the init settings next to it. Sorry. You can see already. So let's go in here. Again, 2D or 3D. We want to go to 3D. However, if I don't know why. So if I go for 1 here and the boundary, I will explain in a second, but if I go for option 2 here, it becomes red. So I don't know why that is, but somehow only that's a value list, so we need to change that one to what was it? Dimension. So 2D would be 1, 0, and 3D 1. Anyone knows why that is? Please let me know. And here the same thing. So we have the bounce, respawn, and none. So again, the value list. Change that, double click, change to bounce equals 0. Respawn equals 1, and none equals 2. So that means that defines the behavior of the agents. So what do they do? Do they bounce when they hit each other, respawn, or none? So I have that behavior in there. So now we're good with this initial settings. We can connect them to the engine and move on to the next. And it's the move settings. Connect these as well. And so we need to introduce some values. So how do they move, in which direction, which vector, which velocity, which speed, max force, stuff like that. So I just give you the numbers here. I think that if you're going to play with these things, you can find out on your own what these settings are doing, but these are kind of the standard settings. So for the beginning, it's just okay to start with it. Later, manipulate them, and it always becomes black or in a different color when it's okay. Okay, so what else? We need behavior, of course. So now we have just to inform them where to spawn and how to move. But what do we want? We want to, here we have this list of behaviors, so we can flock them, so they have these birdish things, they can wander around, they can track paths. That's actually what we need now. So it's like an attraction to that grid here. Here. So they try to orient around these curves, and so we need these lines. So what we're going to do is quickly join them because it's quite heavy otherwise. In the polylines, it's already okay, it says, but let's have some values there. So threshold could be 500. And the distance, so it's about this distance and radius when these curves affect our blocking system. So let's go for 30 for the projection distance, and for the polyline radius we can go for 25. So, but this doesn't go directly in there. So because here, this is actually where the interesting stuff happens. We can connect multiple behavior systems together. So in between, we need a controller. And if we zoom in close enough, there's a plus, and we can add our first behavior. That already says then, okay, multipath tracking, and then we can connect it to the behavior settings. First we go through that, and then I introduce another behavior to make it interesting. And then we need a visual representation. So also Colibra has their own system there. So we go, we want to see the trails of the storm. So we want to have trail data. We need a Boolean toggle here again to say yes, we want that. Then we can chat. Okay. And we have trail step and max trail size. So there we can say how many steps it needs to save the next vector, and also how many vectors we want to have in there. So we go also the standard value, and the step size we go for 0. This is the trail, and then we have the where is it? Visual settings here. So here we can implement the trail, and we need some color for the trail, and gradient color, and we have just the RGB channel here. We can also introduce some texture, but we don't gonna do that. So it needs a domain here. So we're going to construct a domain again, and it always goes from 0 to 255, so that we can define the color space, and we need that 3 times, and connect it to R, G, and B, and we can also say how kind of thickness of the trail, so it should be in between 1 and 3. So here we go, and we need to say something like, okay, we need values of color, so we can later see what it does in the visual representation. Introduce it here, And again, we need here in the display mode, that's important for later on. You can say either it's graphic or geometry. So for now, the graphic is faster to display, but later on we need to, if we are fine with the statics, we need to change it to geometry so we can actually use the trail as path and then to create the geometry out of it. So this says false. So we're almost there with this setup here. We need a button to reset, and we need a timer, of course, to run it. And let's set the interval to 1 millisecond. And oops, drag it onto it. And last thing, we need the cloud display for the creepers. You can see size 24. And if I didn't miss anything, I think we're good. Side stuff. We want to see the. I did already a drawing here. Sorry, guys. This could be interesting. Let's see. Now there's something here. We need 3D. Let's reset it again. There we go. And we need a trail somewhere. All right. Reset it again. And let's see what it does. Okay, it starts somewhere, right? So somewhere in this bounding box. And each agent is looking for a curve and try to walk along this curve and leaves a trail behind it. So of course now it's really random and uninformed, I'd say. But okay, this is how the system works, and we can implement more data later on. So I think it looks cool. However, I want to introduce also another behavior, as I said before. So move that a little lower, and we want to have this wandering behavior. So they're more like confused agents, which go a little left to the right. So we're going to use the weaving wandering here. And so we can also again have some more values in here. The type is quite interesting, so it has different predefined types. I like the third type, so it's number 2. We can have the standard values. I think these are fine actually. 60. No, let's go for 15 for the distance, and 20. Change to 100. That's fine. Again, add another behavior. Reset it. You see already they're going crazy a little more, right? So they're still trying to find the curves, but they have this certain wandering behavior. There are a bunch of options actually in Calibre, so you can introduce it also that it wanders on a mesh and so on. So what is actually missing in this tutorial is the flocking behavior, which is quite interesting. So they have this bird swarm behavior and so on, but you can try later on. So I think for that we're actually quite okay. And now it's actually now quite simple, because we're just going to use the geometry of the trails and insert it into the cocoon, and then have our mesh. But what I mean, we've tried was, okay, we want to have this hybridity, we want to have a system that kind of is this gradient-like geometry. So first, I mean, there are different options. So also I'm working right now on another example, so perhaps I'm gonna share it later on. Now I just use this one swarm set and divide them according to the tractor points. I just show you quickly what I mean. So first we need to stop it for a second and change the display mode to 1. So we get actually geometry. Reset it. Like that guy. Just connect that to the trails. Oops. Sorry, one sec. Now we have points, which is also interesting. Let's see. Oh, yeah, of course, we need to connect these ports. Of course, with interpolate. That minute. So you can see already it's kind of slowing down per cycle. I think we're good. We stop it, don't reset it, because then you delete your swarm. And what we're going to do now is shorten the curves a little. So I'm going to shatter and insert the curve, reparameterize them, and say shorten the first 10%. And select that item. So it looks so different. And let's see. Right. That guy, reverse the list, flatten it. And now we're introducing these two attractor points from the beginning. Here, these two guys. So I want to say the curves, or let's say the end point of the trail, because that is more interesting for me in that case. Which one is closer to point A or point B goes in that list and the other one in the other list. So I have these curves, say endpoints. Check the endpoints for distance from that point and point B. Right, so we get two values. Then I just check if the other one is smaller or not, and simply use a dispatch for that list with the smaller than. There's a lot of text if you have the full name. Yeah. With a list of the curves, of course, from that. Are we still good? I think we're still good. Yeah, cool. So
You stopped it? You stop the simulation?
Yeah, I stopped it, yeah. You need to freeze it here with the timer. I mean, you can also bake it or whatever, kind of like to have all in Grasshopper. So, actually in the beginning I scaled our grid. As you can see, is the base curve. I did that because the values I was working with were working for different scale, but you can also change the values here, but everything basically with distance and radius and so on, you need to change these values according to your scale. So, but I was lazy, to be honest, and so I just need to scale them back to our size. So let's take that and what did I do? Minus, right? Minus x. No, oh, of course not. 1 divided by x, so the factor. So then I scale it back. Let me show you. There we go. We're going to hide everything else we don't need. And we have to size again. And this guy is actually from the last tutorial, so I'm going to hide them. So here we see already we have our 2 sets. And because what I wanted to create is also that if I now go and thicken or geometry wrap all the curves, it's still, you have very long trails here in the middle, and I wanted to have a certain gradient. So according to the attractor points, I wanted to reduce the length of the curves in the middle. So you have very long curves here and shorter and shorter. Of course, because it's a swarm and the agents went maybe from here to there and end up in a different position, it's not 100% reliable. But on the other hand, it's giving a nice randomness in this system. So actually, one last step here. Again, what I do is shorten now the attractors. So I use an endpoints node, and check again the distance from the endpoint to point A again. We can also quickly do a shortcut. Sorry, point, of course. Take point A and point B. Take them. We can introduce them here. So this distance we want to check as well as the other from the other point. And again, the remap comes into play now. So we have this distance values. We define our domain, our source domain with a bounds, and the target we're gonna define ourselves. So that and domain, construct domain. So I think so. It's about shortening. So I think the last 3% and first 1. So everything in between is there. So that's our target. Also going to do the same for the other one. We can leave the domain. So every 2 sets, all 2 sets have the same target domain. So we connect this guy, and now we shatter them again. With the mapped values and the curves of that one set. are these. So these curves go in here. We need to reparameterize them, and we gonna graft both of them. Oops, sorry. Yep. Do the same for the other one. And second set of curves. And again, just select the item, because we just have 2 items obviously in that list. So as you can see, that's what I've meant in the beginning. So it could happen that you have longer curves here. And then check something quickly. You see now in the middle are longer, but if we go that, here you have more condensed. What I did also for the example we've printed, it's like this, but I use more spawn points and yeah, different time of running, so you get denser geometry, obviously. Okay, and then actually we can connect that to the cocoon.
Maybe
sorry.
Yeah.
Yeah. Okay. Yeah. Sorry. Yeah. It's like.
Everyone's lost their
Yeah.
question.
Sina, you're still following?
I'm fully following.
That's good. No, if you have, I don't know, of course, your skills are so, because then just let me know if you're lost.
You can just use your microphone, you don't have to raise your hand. Just use your microphone, and if you have any question in any part, just let us know. Go on.
Probably all like what? I did that like, I don't know, in kindergarten.
No, like I think the idea of especially the first tutorials is also to set the resolutions of printable objects and the scale that we can work with. I think if you are already familiar with like Swarm or Marching Cube or these kind of mesh-based modeling, of course you can be faster, but I think it's also important for us to have an understanding of the scale of the material that we are going to work with, because like in the groups we will have 4 basically focus. One is the like overall design, one is the prototype design where the scales and resolution is really important, whether we are doing a kind of axiotic joint that will be combination of like flexible and hard. In terms of size and resolution, I think these examples would definitely inform the design. So therefore design, prototype design, the second one, and the third one is like a narration and story behind the idea, and the documentation. So I think these 4 working packages, later we will discuss how we can basically benefit from these simple tutorials all the way to the more complex ones. So yes, if you are advanced, be a bit more patient, but maybe you can build on top of this.
Okay, cool. Yeah. Okay, just maybe to quickly finish that now. I introduced the cocoon now. I just used it like a preset here already, because we did that like 5 minutes ago. What I'm gonna do is also remap again these values. So actually remap the remap values, because it doesn't matter. Where is it here? This guy, let me see. Okay. There. And connect that to this guy. And the source is that old target. Again, the same for this, and also here the second set of curves. So we're gonna charge them again, the curves individually according to the tractor points A and B. That's what I did. I just used the same values because the distance stays the same. However, I need a different target for the charge of the curves. So connect the curves. Wait, I think let's flatten them. And that guy goes in here. We have the cocoon engine. Maybe we can see already something happening here. And we see, okay, these values seem to need a little more, yeah, that's not what I did, okay, yeah. Need a little tweaking. So I think we're gonna change the radius, the chart radius a little. Let me do something. Just lock the solver to 9 maybe, and strength is okay. Let's reduce the ISO. See what happens. Okay, I mean it's not really what we printed and showed you, but it's the same setup. So if we introduce more agents, we get a nicer geometry out of it. We can refine it because this is not what we really like. It takes a second to do that. So that's why I also said in the beginning, it's really important just to start with low counts. And otherwise, if you add already like 5 different behaviors, 1,000 of spawns, and then a high resolution mesh in the end, it's either on the one hand, it's hard to track what each value does, and also it takes forever, and you don't make any progress. So maybe it's a general thing, but I always do this mistake. Like, hey, let's crank up the values and see what it does. Yeah. Okay, here's some problem somewhere. This is what it sometimes does. If the mesh is not really the cocoon mesh, it needs something, some different values. So also change the ISO here. So there it's like sometimes a little playing around with the values. And actually that's about that. And I think let me bring something on the screen. Oops. There we go. Here we have nice mesh. And of course the one that I'm going to show you in a sec that we printed is that guy. So you see it's thicker here and here, gets less and less in the middle, and we have this single parts FGM-like gradient distribution of 2 materials. I think that would be that for Grasshopper. I mean, if you have any questions or something, you can also text in a group, text us privately, whatever, I think, or say it now. But as Sina said, it's like the base. If you're more advanced, you can maybe build on top of that. If you know other systems, how to create swarms or geometry, of course, use it. Also, Quelia is a nice swarm system, and also in the folder, in the Google Drive folder with all the plugins, we used only 2 or 3 of them today, but it's just a nice list of different plugins you can use. And I think that's from the Grasshopper side, right?
I have a question with regards to the big geometries. By any chance, are they overlapping? As in, if you create a volume between the two, are there any volumes which are like overlapping each other, or are they separate in a way?
These guys, yeah, they're intersecting a little. So what would be interesting to solve is, of course, that these two swarm sets avoid each other, and somehow through geometry wrapping, you still can create like two geometries without Boolean operations.
Thank you.
Wait, can you see? Like, yeah, whatever. So you see it's inside as well.
Yeah, so what we had in mind for this one was either like a penetration of a hard material inside a flexible or inside a transparent material. But another idea is to have them fully avoiding each other, which somehow will be the case in the last tutorials in Houdini, where we are thinking of A and B, so where they are fully like intertwining but not colliding. So I think the combination of these hybrid systems at the end can be applied. Maybe just to if you stop sharing, Benny. I think it would be nice later on if you are interested to know more about the background of these methods that we discussed.